the spin-Hall effect experiment to try to convince you that this is a measurable physical quantity. You can measure physical consequence if you have a motion for spin current. In the spin-Hall effect, you will have magnetic moment piling up at the edge of your sample, and that's magnetic moment you can of course you can measure. Now that we can also discuss other important physical consequences. If you have a spin motion, you have a spin transport. Again, we can make a comparison with charge transport. If you have a charged particle moving, what will happen? If you have a charged particle sitting there, it will create electric field, right? You have a charge, you will, in the surrounding of the charged particle, you will have an electric field due to this charged particle. But if the charged particle moving, just that you have a charged current, you will create magnetic field, right? The source of magnetic field is due to the motion of the charged particle, due to the current. So the charge motion will create magnetic field. Now, what happens if you have a spin motion, spin current? What will happen? So, naively gas will create electric. Okay. Charge motion will create magnetic field. Spin motion will create electric field. Okay. So why it will create electric field? Again, that's just use a physical picture. Spin motion, the naive physical picture, is that spin up moving one direction, spin down moving opposite direction. Spin up is just a magnetic dipole, right? If you have magnetic dipole in space, okay, they will create magnetic field, right? If you have magnetic dipole, it will create a magnetic field. Okay. Now, if this magnetic dipole is make its own motion, apart from the magnetic field it creates, it will also create electric field, because you have this v velocity cross divided by speed of light cross of its its magnetic field. So this is so-called Lorentz transformation, right? If you have moving, if your source is moving, apart from creating magnetic field, you will also create electric field. Go with it. Now the spin motion, the picture is spin up, moving one direction, spin down, moving opposite direction. Okay. So spin up, spin down, they create their different magnetic field. The magnetic field is in opposite directions. So the net magnetic field from spin up and spin down will cancel out. But that electric field, because velocity also different, magnetic field have a different sign. Velocity also has different sign, moving in the opposite direction. So that electric field, you just add up some of these two pieces from spin up and spin down. So that electric field is non-zero. So if you have a pure spin current, it won't create a magnetic field, but it will create electric field. So of course, electric field is a measurable physical quantity. So you can detect the electric field if you have a spin transfer. So you can find the electric field. So in our previous work, we were able to derive, suppose you have this linear spin current, okay, the source of, that is also source of your electric field. It will create an electric field. Okay. And more importantly, the angular spin current I defined before will also, this angular spin current will also create an electric field. So the total electric field, if you have a spin motion, normally the spin motion has a linear part and a rotational part. Both of these will create electric field. And it's the total electric field, sum of these two will satisfy the Maxwell equation. Okay. Will satisfy Maxwell equation. So the expression actually is quite simple at the end. Okay. So this is so for many of the graduate students, you probably have taken this Jackson E&M class, and if you look at the equations there, quite some of the equations are very similar to this expression. So it's very simple. So of course the source of electric field, like the net electric charge, will be source, and also here we mentioned that the spin motion, spin current is also a source of the electric field. So I have mentioned that in the spin transport, different from the charge transport, normally you have this rotational motion. So the spin, due to the external magnetic field or due to spin orbital interaction. So if that's the case, in the spin transport, the spin is not conserved quantity, not conserved due to this rotational motion. Okay. But if you insist that whether it is possible to find a conserved quantity in the spin transport, okay. So if you insist whether it's possible to find a conserved physical quantity in the spin transport, it turns out you can do that. Okay, it turns out you can do that. Mathematically, actually, it's quite simple. Suppose you have this quantity here. If you mathematically, if you apply a divergence operator on these equations, okay. If you apply a divergence operator on these equations, okay, and mathematically you can carry out this, then you can define another current, which is a combination of this linear spin current and angular spin current, okay, and through this combination, this current, which we call the current for the divergence of this S here, it is a vector, and the divergence S, of course, S is a vector. Divergence of S, sorry, is a scalar. So here is a vector, okay, and which is a linear combination of this, and this is conserved. So it tells us in this, even in the spin transport, although spin itself is not a conserved quantity, but the divergence of the spin is a conserved quantity. And associated with this divergence of this, there's a current, which is a combination of this linear spin current and the angular spin current. You can find a new current. Then you can ask what is, so this is conserved, divergence of S is conserved. Okay. Then you can ask if it's a conserved quantity, what's the physical meaning of this current? What's the physical meaning of this current? It turns out this is really is the source which creates the electric field. So as I mentioned, in the spin transport, both linear spin current and angular spin current can create electric field. And the way they create the electric field, actually, is through this current. Okay, it's a combination of this. So this divergence of S, this current, actually is the source which creates the electric field. So that's a well-defined physical quantity. You can. So this is the source which gives rise to electric field. Okay, so divergence of S, divergence of spin is a conserved quantity. The current in this continuity equation, there's a current associated with the divergence of S. That current is the source which gives rise to the electric field. That is the some kind of linear combination of what we had before, linear spin current and linear spin. Okay. So this is some basic properties of spin transport. I try to discuss this in comparison to a charge transport, particularly from this sort of type of a continuity equation. So up to now, I try to introduce this concept of this spin current, and I try to convince you it's a measurable physical quantity. You can use like spin effect to measure this spin current and so on. Now, if you have this physical quantity called a spin current, the question you can ask whether you can make a superfluid out of this current. Okay. Basically, whether if you have spin transport, can you make a spin superconductor or spin superfluid from this spin motion? Okay. So we propose this idea of a spin superconductor or spin superfluid, and physically we find a concrete system that is the ferromagnetic graphene, which we believe you can see this spin superconductor. Okay. So remaining of the discussion will concentrate on this spin superconductor concept of spin superconductor. So again, we want to make a comparison with the charge superconductor. Charge superconductor, let's just talk about the simple case, so-called low TC superconductor, low temperature superconductor. Normally it's S wave two pairs. Okay, so you have to form a bosons. So from 2 electrons. Okay, so it has a charge of 2e, and normally it's S wave. The S wave tells you the spin, total spin, because each electron is spin half. So the 2 electron can have a spin 0 or 1. And the S wave tells us the spin is singlet, spin is 0, and spin singlet. And the wave function, the symmetry, all the parameters is symmetric in different directions. It's isotropic. Okay, so it's S wave. And we have a well-known BCS ground state described as superconductor, BCS superconductor. Now, in this ferromagnetic graphene, we want to have a spin superconductor. Again, in order to achieve a superconductor, it has to be a phenomenon of BEC, boson-Einstein condensation. So you have to achieve a boson first. Okay. In the Cooper pair, it's 2 electrons. In the ferromagnetic graphene, the spin superconductor is so-called excitons. Okay. Exciton, it consists of 1 electron and 1 hole. Okay. 1 electron, 1 hole, and it's also a boson. And electron and hole carries different same amount charge but a different sign. So the net charge is 0. The charge is 0. And again, electron and hole both spin half. So it's possible to have a spin singlet and a spin triplet. So if under certain conditions you achieve a spin triplet, that is a spin 1, then what happens? If you have an exciton which is boson with a net spin 1 but without the charge. So if you have a spin 1 boson which make a condensation, which only has a spin, that will give you a spin superconductor. So here in the solid state or condensed matter system, we use ferromagnetic graphene as an example. But you can extend your thinking that if you have a cold atom, right, with a spin 1 and make with charge 0, if you make a condensation out of it, it will be a nature candidate for spin superconductor. It's just that in the cold atom system, the experiment ways to tell the property of physical property of the system is very limited. Unlike the condensed matter system, you have many ways of detect the different physical properties. You can do transport measurement, optical measurement, and so on, many different ways. In the cold atom systems, the ways of doing physical measurement is kind of limited. So anyway, so if it's a spin triplet exciton condensation, is what we call the spin superfluidity or spin superconductor. So then so the story sounds quite simple. It's just exciton, right? So you already know that we have come across excitons in many condensed matter system before. Right? Normally, in a semiconductor or insulator, you do have excitons. Why this thing is not supposed to be formed? So the reason is that in normal semiconductor or insulator, it's like this. You have a band gap, separate the conduction band and the valence band. Normally you use light to shine the light on your system. There may be electron transition from the valence band to conduction band. You have some electrons here and create holes in the valence band. So you have electron and holes. And they have attractive interaction due to their Coulomb interactions. And then they may form a bond state, which is called excitons. But in this case, the lifetime of this exciton is relatively short. The electrons want to go back to recombine with the holes, such that to save the energy. So the ground, this is the metal stable state. The ground state, all the electrons wants to go back, such that recombine with the holes to lower the total energy of your system. So that's a lifetime issue. So typically it's a picosecond range for the exciton. It's very hard to do many measurements within this short period of time. So it's unstable. And also excitons in normal graphene, it's also have been seen. And in this case, the excitons are spin singlet, spin zero. It's not a spin triplet excitons. Okay. That have been seen in normal graphenes. So ferromagnetic graphene, there's some difference here. So here I draw a schematic picture of these ferromagnetic graphenes. So of course, graphene is direct particles, so it has linear dispersion relations. So we use direct point to represent this energetic plot of the graphene. And the ferromagnetic graphenes that spin up and spin down as a separation. So direct points of spin up and spin down are separate in energy. Okay, one is above the other. Okay, like this situation. So of course you can imagine that you can achieve this situation if you just apply a magnetic field to your graphene system, right? Due to the Zeeman energy, spin up and spin down, where it has a Zeeman shift. So there will be energy difference between the direct points of spin up and spin down. However, if you do estimation, you will find this energy shift is very, very small. Okay, between these direct points, it's very small. Okay. So in order to have an energy shift of order of like MeV, you have to apply magnetic field of like at least hundreds of Tesla, or maybe thousands of Tesla. So which is impossible. Okay. However, if you have a ferromagnetic graphene, one way of achieving ferromagnetic graphene is by growing graphene on a ferromagnetic material. Okay, I get a better candidate like a ferromagnetic insulator. Okay, Then ferromagnetic insulator, there's an exchange field due to ferromagnetic insulator. That exchange field, if you estimate, it's very, very high. Normally it's of the order of 1,000 Tesla. So if that's the case, then you can have, if you are able to grow the graphene on ferromagnetic insulator, then you will achieve ferromagnetic graphene. So so as soon as the graphene appeared, people already try to grow ferromagnetic graphene. The purpose of that is not for achieve a spin superconductor, it's for achieve a Spintronics applications. You want to have a graphene, you wanted to have this carrier in graphene have a spin properties. So they try to achieve a ferromagnetic graphene for that purpose. But if you can do, if you can do a ferromagnetic graphene, then what we propose that it is also to steer what we call a spin superconductor. So there are already some experiment evidence of achieve a ferromagnetic graphene. So, but it's not definite yet. So it's still ongoing subfield in condensed matter. So if you achieve a ferromagnetic graphene, okay, and you have electrons, you have holes, and the electrons have but it's from a different spin components. Okay, from different spin components. Then if this is the case, this does not have this recombination issue. Recombination, so electron has a high energy, holes has it's in valence band. They don't want to recombine. Okay, in the normal semiconductors. But in this case, there's no recombination. If you recombine, it will cost the energy, right? For the low energy electrons to this band. First, you have the spin flip, then you have to also create. It will increase the energy. So it does not have a low recombination issue. So if this is the case, it will be a stable equilibrium problem. It's not a matter stable state. So we propose in this system, if you can create a ferromagnetic graphene, you will have a spin superconductor. So of course we have to do some calculations to support this idea. Okay. So this mathematics I won't talk about in detail, but I will just mention that it's very similar as what the BCS theory for charge superconductor. So here you can write down what the Hamiltonian for ferromagnetic graphene. Okay, that's H0. Then you have a Coulomb interaction between the particles and the holes, between the after the calculation, so let me tell you the basic result of the calculation. So without this Coulomb interaction, electron-electron interactions, the ferromagnetic graphene, the band structure is just these blue curves. There's a separation of the direct tone, direct parts. Then it's linear dispersion. This relation. The important thing is that there's a crossing here and here. And this crossing point, energy is sort of degenerate, right? Then the Coulomb interaction will play important role because once you have degenerate, the other part of the Hamiltonian will be important. And the Coulomb interaction, attractive interaction between particle and the hole, will create energy gap around these crossing points. That gives you this black curve. Okay, black curve. So, due to this creation of this energy gap, this is the gap for spin superconductor, just like the energy gap for charge superconductor at the Fermi surface. There's an energy gap. Here you also have an energy gap. Below this energy gap, it's a ground state is a spin superconductor. So this is the. Let me skip this. And again, you can similarly estimate what is this energy gap. Okay, you can self-estimate this energy gap. So here, let me show you one picture of this energy gap as a function of m. Here, m is the separation of these two direct points due to the exchange field from ferromagnetic insulator. So it depends on what's the order of your m, then you have this energy gap. Okay, so order of this is both of these orders MeV. Okay, so you have this energy gap. Okay. Now, so far I tried to introduce this concept of spin superconductor. It's basically if you have boson with spin, non-zero spin, spin 1 or spin 2, whatever, then if you make a condensation of this boson, it is a spin superfluid, spin superconductor state. Okay? And we propose like a ferromagnetic graphene is a possible candidate to have this boson 1 system. Basically boson 1 spin triplet excitons. Okay. If you have a low enough temperature, due to this attractive interaction between particle hole, it will opens up a gap. So once it opens up a gap, below the gap is the ground state spin, is the spin superconductor. But in terms of charge, due to this energy gap, the charge in terms of charge is a semiconductor or it is an insulator. Okay, due to the opening up of the gap. Okay, so it's a spin superconductor, but in terms of charge, it's an insulator. Now, what is the physical property if you have a spin superconductor? We know that if there's a charge superconductor, there are two basic properties. Charge 2, or you can say there are two perfectness of a charge superconductor. One is that the perfectness is a perfect conductor. Resistance goes to 0. Conductivity goes to infinity. Okay? So it's a perfect conductor. So that's not enough, right? If it's just this property, you could have a metal, perfect metal, will have this property, but the perfect metal is not a superconductor. So another perfectness is a perfect diamagnet. It's a perfect diamagnetic material. Okay. So basically it's the Meissner effect. So these two properties give us this charge superconductor. And these two properties can be derived from so-called London equations. London was able to first write down two equations to describe this charge superconductors. So the first equation, basically, it's the charge density time derivative is proportional to the electric field. The second property is the Q of charge current. So charge current density time derivative property in electric field. Q for the charge current is property in full magnetic. So the first equation, charge current, we know that the velocity operator is E times V, right? Velocity. So velocity time derivative is equal to acceleration, right? Equal to acceleration. And the acceleration is proportional to the electric field. Because if you have a charge, if you have electric field, there's a force, Q times E, right? The force equals the electric field. So this is basically just Newton's second law. The acceleration equals the force. Right? But this is not this simple. The very fact you can write down this for charge superconductor tell us is you have no damping, no resistance.